In 2004, Yamaha did something that engineers called impossible. They took an inline-4 engine, gave it a V4 soul, and created a machine that would rewrite the rules of MotoGP forever. This is the story of how the YZR-M1's revolutionary crossplane crankshaft didn't just win races, it broke the entire sport.
Unfortunately, the video quality is poor, low resolution, shot from a distance, and the entire bike is covered in matte black.
It's 2002, and MotoGP has just undergone its biggest transformation in decades. The legendary 500cc two-stroke era is over, and now everyone's scrambling to master the new four-stroke formula. Honda dominates with their V5 RC211V, a machine so advanced it seemed to come from the future. Ducati was working feverishly on their L4 Demolishing, a 90-degree V4 that promised Italian flair combined with cutting-edge technology. Most manufacturers were convinced that V-configuration engines were the only path to victory. The reasoning was sound. V4 engines offered superior mass centralization, better packaging around the chassis, and most importantly, the ability to create uneven firing orders that improved traction in the critical corner exit phase of racing. But Yamaha? They had a different idea entirely, one that would challenge every assumption about motorcycle engine design. While their competitors chased complex V4 and V5 layouts, Yamaha's engineers were locked away in their Iwata research and development facilities, working on something that would make veteran engine designers scratch their heads in disbelief. Led by chief engineer Koichi Tsuji, the team was attempting something that violated fundamental principles of motorcycle engine design. They wanted to put the firing characteristics of a V4 engine into the compact package of an inline-4. But why was everyone convinced about this being almost impossible? The answer lies in the fundamental physics of internal combustion engines and the specific demands of motorcycle racing. Traditional inline-4 engines fire in a predictable pattern: cylinder 1, then 3, then 4, then 2, with each cylinder igniting every 180 degrees of crankshaft rotation. This creates what engineers call an even firing order, where power pulses are delivered at perfectly regular intervals. The result is smooth, linear power delivery that feels refined and controllable, perfect for road bikes where comfort and predictability are paramount. But in MotoGP, predictable isn't always what you want. When you're trying to put 250-plus horsepower through a contact patch the size of a credit card while leaned over at 60 degrees, tire management becomes everything. The rear tire needs micro moments to regain grip between power pulses, especially when exiting corners where races are won and lost. V4 engines naturally provide this through what's called a big bang firing order. Instead of evenly spaced power pulses, V4 cylinders can be timed to fire in quick succession, followed by a longer pause. A typical V4 might fire cylinders 1 and 2 almost simultaneously, pause, then fire cylinders 3 and 4, creating bursts of power followed by brief moments where the rear tire can regain traction. Here's why Yamaha's plan seemed impossible. Inline-4 engines, by their very geometry, shouldn't be able to create this effect. The crankshaft throws in a traditional inline-4 are spaced 180 degrees apart, locked into that even firing pattern by physics and packaging constraints. To create uneven firing, you'd need to completely reimagine the crankshaft design, but doing so would create catastrophic vibration issues. The vibrations in an inline-4 are carefully balanced by the even firing order and reciprocating mass arrangement. Change that firing order, and you'd create what engineers call rocking couples and primary imbalances that would shake the engine apart. The crankshaft would need to be heavier to handle the uneven loads, the engine mounts would need to be stronger, and the entire motorcycle would vibrate like a paint mixer. Every engineering textbook said it couldn't be done. Every computer simulation showed it would fail. Every experienced engine designer knew it was madness, and that's exactly why Yamaha decided to do it. The breakthrough came when Yamaha's engineers realized they didn't need to fight the unconventional firing order. They needed to embrace it and engineer around its challenges. The solution was the crossplane crankshaft, a design concept that had been used in V8 engines for decades, but never successfully applied to a motorcycle inline-4. In a crossplane design, the crankshaft throws are arranged at 90-degree intervals instead of the traditional 180-degree spacing. For the YZR M1, this meant throws at 0, 270, 180, and 90 degrees, creating a firing order of 1-3-2-4 with intervals of 270 to 180 to 90 to 180 degrees. This seemingly simple change fundamentally altered everything about how the engine delivered power, incorporating a balance shaft system to manage the unusual vibration characteristics. The connecting rods had to be redesigned to handle the uneven loads created by the irregular firing pattern. The engine cases required additional reinforcement. Even the oil circulation system needed modification to ensure proper lubrication despite the unusual crankshaft dynamics. Computer modeling showed the engine would produce 15% more vibration than a conventional inline-4. The additional rotating mass would hurt acceleration. The more complex crankshaft would be expensive to manufacture and potentially less reliable. On paper, Yamaha was making their engine objectively worse in almost every measurable way. But there was one measurement that mattered more than all the others: how it would feel to a rider at the absolute limit of performance. When Valentino Rossi first threw his leg over the prototype M1 at the Valencia test in November 2003, something magical happened. Rossi, already a three-time world champion, had an almost supernatural ability to feel the subtle differences in motorcycle behavior. Within 5 laps, he knew Yamaha had created something special. The crossplane engine's unique power delivery gave Rossi feedback that was simply impossible to achieve with traditional firing orders. Instead of the linear power build of Honda's RC211V, the M1 delivered power in waves that seemed to breathe with the tire's grip levels. Working alongside legendary crew chief Jeremy Burgess, a man who had guided Wayne Rainey and Mick Doohan to world championships, Rossi began to unlock the M1's true potential. Burgess, initially skeptical of Yamaha's radical approach, quickly became a convert when he saw the lap time data. The crossplane engine allowed Rossi to ride in ways that seemed to defy physics. Where other riders had to be cautious with throttle application mid-corner, Rossi was rolling on power earlier and more aggressively. The engine's natural power pulses were acting like a primitive form of traction control, giving the rear tire micro-recovery moments that allowed for earlier and more aggressive acceleration. But how exactly did this impossible engine give Yamaha such a massive advantage over Honda's proven V5? The answer lay in something Yamaha's engineers discovered almost by accident during testing. The crossplane firing order didn't just change when power was delivered. It fundamentally altered how the rear tire interacted with the track surface at the molecular level. In traditional engines, power pulses arrive at regular intervals, creating constant loading on the rear tire. This consistent load can cause the tire to heat up and lose grip, especially during long corners or when the bike is already at maximum lean angle. The tire essentially gets overwhelmed by the constant demand for traction. The M1's crossplane engine delivered power in a completely different pattern. The 270-degree gap between the first and second cylinder firing created a longer pause where the tire could actually cool slightly and regain grip. Then came the 180-degree gap, followed by the shorter 90-degree interval, creating what tire engineers call a grip recovery cycle. This wasn't just theory. Yamaha's telemetry data showed that M1 riders could maintain higher corner speeds in earlier throttle application than their competitors. The engine was essentially giving the tire a split-second break between power demands, allowing it to maintain optimal grip levels even under extreme conditions. But the real secret was even more profound. The crossplane engine was teaching riders to ride differently. The unusual power delivery forced riders to smooth out their throttle inputs, to work with the engine's natural rhythm rather than fighting against it. This created a riding style that was not only faster, but also less taxing on the tires, allowing for more consistent performance over race distance. Rossi, with his incredible sensitivity to motorcycle dynamics, was the first to truly understand and exploit this characteristic. He learned to time his throttle inputs to match the engine's natural power pulses, essentially becoming one with the machine in a way that his competitors couldn't replicate. When the 2004 season began at Welcome South Africa, the motorsport world held its breath. Could Yamaha's unconventional approach really challenge Honda's dominance? The RC211V had won 3 consecutive manufacturers' championships and seemed unbeatable. The answer came in dramatic fashion. Rossi didn't just win the opening race, he demolished the competition, crossing the line 10.4 seconds ahead of Honda's Max Biaggi. But more impressive than the margin of victory was how he achieved it. Lap after lap, Rossi was hitting apex speeds that seemed impossible for the track conditions, carrying corner speed that defied conventional wisdom about motorcycle physics. The paddock was stunned. Seasoned engineers who had dismissed Yamaha's crossplane concept as a gimmick were suddenly scrambling to understand what they were witnessing. Television commentators struggled to explain how Rossi was riding lines that would have been suicidal on any other motorcycle. Race after race, the pattern repeated. At Jerez, Rossi won by over 15 seconds. At Le Mans, he led every single lap from pole position to checkered flag. The M1's cross-plane engine was allowing him to ride in a style that was uniquely his own. Impossibly late on the brakes, impossibly early on the throttle, and absolutely committed through every corner. The technical data told an incredible story. Compared to the Honda RC211V, the M1 was carrying 3 to 4 miles per hour more speed through medium-speed corners. Rossi was able to pick up the throttle a full 10 to 15 degrees earlier in corner exit phases, gaining tenths of a second per corner. Over a lap, these tiny advantages added up to margins that seemed almost unfair. By mid-season, Honda was in panic mode. They had the faster bike on paper, better electronics, more horsepower, and a larger budget. But none of that mattered when Rossi could simply carry more speed through the corners that defined lap times. Honda's engineers began frantically experimenting with different firing orders and engine characteristics, but they were playing catch-up to a philosophy they had never considered. Let's dive deeper into exactly what made the YZR-M1's crossplane inline-4 so revolutionary. The engine displacement was 990 cubic centimeters, the maximum allowed under 2004 regulations, with bore and stroke dimensions of 79 millimeters by 50.9 millimeters. These relatively short stroke dimensions allowed for higher RPM operation, with the M1 revving to over 16,000 RPM. The crossplane crankshaft itself was a masterpiece of engineering precision. Each throw was precisely positioned to create the 0 to 270 to 180 to 90 degree arrangement. But the devil was in the details. The crankshaft pins were offset to accommodate the unusual firing pattern, with each journal precisely machined to tolerances measured in thousandths of a millimeter. The connecting rods were forged from ultra-high-strength steel alloys, with each rod individually balanced and matched to ensure perfect engine harmony. The pistons were custom designed with unique compression ratios for each cylinder to optimize the power delivery characteristics of the crossplane firing order. But perhaps the most impressive engineering feat was the counterbalancing system. Traditional inline-4 engines are inherently balanced in terms of primary forces, but the crossplane design upset this natural balance. Yamaha engineers incorporated a sophisticated balance shaft system, running at twice crankshaft speed to eliminate the additional vibrations created by the uneven firing pattern. The cylinder head featured Yamaha's most advanced valve train technology, with titanium valves, pneumatic valve springs, and finger-follower rocker arms that reduced reciprocating mass. The intake ports were individually tuned for optimal airflow, while the exhaust system was designed to extract maximum benefit from the crossplane firing order. The fuel injection system was equally sophisticated, with each cylinder receiving its own throttle body and injector. The engine management system could adjust fuel delivery and ignition timing individually for each cylinder, allowing engineers to fine-tune the power delivery characteristics with incredible precision. Power output was conservatively rated at 240 horsepower, but dyno testing suggested the actual figure was closer to 260 horsepower at peak RPM. More importantly, the torque curve was unlike anything seen before in motorcycle racing. Where traditional engines showed relatively linear torque delivery, the M1's crossplane engine produced a curve that pulsed and breathed, creating the unique power characteristics that made it so effective on track. The success of the M1's crossplane design sent shockwaves through the entire MotoGP paddock. Honda, who had dominated the sport for 3 consecutive years, suddenly found their technical advantage evaporating. Their response was swift and dramatic. Honda's engineers began experimenting with big bang firing orders on their RC211V, attempting to replicate the M1's corner exit advantages. They tried different crankshaft configurations, altered their engine management strategies, and even experimented with variable firing orders that could change based on track conditions. Ducati, meanwhile, began investigating how to optimize their L4 engine's naturally uneven firing characteristics. They developed new engine management software that could vary the timing between cylinder banks, essentially creating a programmable Big Bang effect. Even Kawasaki and Suzuki, who weren't yet competing in MGP, were taking notes. When they eventually returned to the Premier class, both manufacturers incorporated lessons learned from Yamaha's crossplane revolution into their engine designs. But the influence extended far beyond just engine design. The M1's success forced every manufacturer to reconsider their approach to chassis design, electronics development, and even rider training programs. The crossplane engine had proven that raw power numbers weren't everything, that the character of power delivery was just as important as peak output. When Jorge Lorenzo joined Yamaha in 2008, many questioned whether he could adapt to the M1's unique characteristics. Lorenzo's riding style was fundamentally different from Rossi's. Where Rossi rode with passion and intuition, Lorenzo approached racing with scientific precision and methodical analysis. The young Spaniard spent countless hours studying telemetry data, working with Yamaha's engineers to understand exactly how the crossplane engine's power delivery affected tire performance, chassis dynamics, and ultimately lap times. His approach was almost academic in its thoroughness. Lorenzo discovered that the M1's crossplane engine could be optimized for a completely different riding style. Instead of Rossi's late-braking, aggressive corner entry approach, Lorenzo developed a technique based on maintaining higher minimum corner speeds in earlier, more gradual throttle application. The results were spectacular. Lorenzo's corner speed data showed he was carrying even more velocity through long, sweeping turns than Rossi, while his tire wear rates were consistently lower. He had found a way to extract the crossplane engine's benefits while minimizing tire degradation, crucial for races that increasingly emphasize tire management. By 2010, Lorenzo had won his first world championship, proving that the crossplane engine wasn't just a tool for one type of rider, it was a fundamentally superior design that could be adapted to completely different riding philosophies and techniques. Here's where our story takes its most unexpected turn, revealing how Yamaha's engineering triumph created a problem they never saw coming. The M1's crossplane engine was so uniquely effective that it fundamentally broke the rider development model that had existed in motorcycle racing for decades. Traditional MotoGP bikes rewarded riders who could adapt to the machine's characteristics. But the M1 was different. It didn't just require adaptation, it required a complete philosophical change in how riders approached the act of racing. The crossplane engine's unusual power delivery created what insiders began calling the Yamaha divide. Riders like Rossi and Lorenzo, who could instinctively understand and work with the engine's unique rhythm, became almost supernaturally fast. But riders who tried to fight the engine's characteristics or ride it like a conventional machine struggled dramatically. This created an unprecedented situation in MotoGP, a motorcycle that was simultaneously the most forgiving and the most demanding ever built. In the right hands, the M1 was incredibly confidence-inspiring, allowing riders to push beyond normal limits with remarkable safety margins. But in the wrong hands, it could be bewildering and unpredictable. The twist became apparent when other talented riders joined Yamaha and struggled to extract the M1's full potential. Riders who had been competitive on Honda or Ducati machinery found themselves fighting the Yamaha's unique characteristics. The bike wasn't just fast, it was fast in a way that required learning an entirely new language of motorcycle control. This created a talent bottleneck that Yamaha hadn't anticipated. They had built the ultimate racing machine, but only a select few riders could unlock its secrets. The crossplane engine's advantages were so specific and so profound that finding riders who could exploit them became almost as important as developing the technology itself. Even more surprising, some of MotoGP's most successful riders struggled with the M1. Champions who had dominated on other manufacturers' bikes found the Yamaha's power delivery confusing and counterintuitive. The very characteristics that made it so effective for riders like Rossi and Lorenzo made it nearly impossible for others to reach their full potential. This unintended consequence fundamentally changed how MotoGP teams approach rider selection and development. Yamaha couldn't just hire the fastest available rider. They had to find riders whose natural instincts and riding philosophy aligned with the crossplane engine's unique demands. Today's YZR M1 represents over 2 decades of evolution built upon the original crossplane foundation. The current 1000cc iteration produces over 270 horsepower and weighs just 157 kilograms, making it one of the most powerful motorcycles ever built. But raw numbers tell only part of the story. Modern electronics have been layered onto the crossplane engine concept with surgical precision. Traction control systems work in harmony with the engine's natural power pulses, creating an almost telepathic connection between rider input and bike response. Launch control systems optimize the crossplane firing characteristics for perfect hole shots off the starting grid. The seamless shift gearbox, introduced in 2013, maintains the crossplane engine's unique power delivery characteristics even during gear changes. Traditional gearboxes create brief interruptions in power during shifts, but the seamless system keeps the crossplane rhythm unbroken, maintaining traction and momentum through acceleration zones. Anti-wheelie systems have been calibrated specifically for the crossplane engine's power characteristics, preventing front-wheel lift while maintaining the aggressive acceleration that made the original M1 so effective. The system recognizes the engine's power pulse patterns and adjusts intervention accordingly. Even the fuel injection system has evolved to take advantage of crossplane characteristics. Individual cylinder tuning allows engineers to fine-tune the power delivery of each cylinder independently, creating custom power curves that can be adjusted for different tracks, weather conditions, and tire compounds. The M1's influence extends far beyond MotoGP, fundamentally changing how the motorcycle industry approaches performance engine design. The crossplane concept has influenced everything from superbike development to the creation of electronic rider aids that are now standard on high-performance motorcycles. The technology transfer from the M1 to production motorcycles has been unprecedented. The 2009 YZF-R1 became the first production bike to feature a crossplane crankshaft, bringing world championship technology directly to the street. The production crossplane R1 created a new category of superbike, one that prioritized rider connection and feel over raw power numbers. Since the introduction of the crossplane engine in 2004, Yamaha's success in MotoGP has been nothing short of extraordinary. 7 riders' championships, 6 manufacturers' titles, and over 100 race victories tell the statistical story of the crossplane revolution. The consistency of Yamaha's success is perhaps even more impressive than the peak achievements. While other manufacturers have had periods of dominance followed by years of struggle, the crossplane M1 has remained competitive across regulation changes, tire supplier switches, and electronic system overhauls. So here's my question for you. If you were designing the next generation of MotoGP bikes, what impossible idea would you pursue? Would you stick with proven solutions, or would you dare to break the rules like Yamaha did in 2004? Drop your thoughts in the comments below and make sure to hit that subscribe button because we've got plenty more racing mysteries to uncover. Until next time.